In this video, we are going to discuss one of the most commonly used PMI technique, that is portable XRF. So XRF means X-ray fluorescence. The portable XRF is widely used in refineries, petrochemical plants, fabrication shops, and site inspections because it is fast, portable, and gives immediate alloy identification. So today we will understand how portable XRF works and what output we get and what elements it can detect and its blind spots and surface preparation requirements and important safety precautions. First we will understand how portable XRF works. So portable XRF works based on a simple principle, that is excites and emits. So the XRF equipment has an X-ray source. When we place the XRF analyzer on the material surface and start the test, the X-ray source sends primary X-rays into the sample. These primary X-rays excite the atoms present in the material. When the atoms become excited, they release energy back in the form of characteristic fluorescence X-rays. So each element gives a different characteristic signal. So for example, chromium gives one type of signal, nickel gives another signal, and molybdenum gives another signal. So the detector inside the XRF analyzer reads these signals and converts them into chemical composition result. Okay, so the diagram 1 explains XRF exit and emit. So now let us look at diagram 1. This diagram shows the working principle of portable XRF. On the left side, we have the handheld XRF instrument. Inside the instrument, there are two main parts. One is X-ray source, the another one is detector. So commonly an SDD detector, which means silicon drift detector. Okay, SDD means silicon drift detector. From the X-ray source, the instrument sends primary X-rays toward the alloy samples. So this is on the right side, we have the alloy sample. Okay, the alloy sample is shown on the right side. So when these primary X-rays hit the alloy sample, the atoms inside the sample get excited. So then the sample emits characteristic fluorescence X-rays back toward the instrument. So these returning signals are received by the detector. So below this diagram, we can see one small bar chart. This represents the output from the detector. The instrument analyzes the signal intensity and identifies the elements present in the material. Finally, XRF gives us the result as element percentage and or material grade match. For example, the result may show chromium, nickel, molybdenum percentages, and the instrument may identify the grade as 316 stainless steel. So the diagram 1 is explaining one key point. XRF does not cut the material. It checks the surface by sending X-rays and reading the returning fluorescent signal. That's why it is very useful non-destructive PMI method. The next topic is output. Output from portable XRF. The output of portable XRF is usually displayed in two ways. The first is it gives chemical composition of percentage. For example, chromium percentage and nickel percentage and molybdenum percentage. Okay, and other detectable alloy method. Second it may be give a grade match. For example, 304 stainless steel and 316 stainless steel or other alloy grades. But we must remember one important point. The grade match depends on the instrument library, calibration, surface condition, and testing procedure. So the inspector should not blindly depend only on the grade name. The element percentage must also be reviewed. The next topic is range of portable XRF. So portable XRF can detect many metallic elements. This elements mentions detects Mg2U. So that means modern portable XRF can detect elements from magnesium to uranium, including silicon. Okay, so this is useful for alloy verification because many engineering alloys are identified based on elements like chromium, nickel, molybdenum, and titanium, and copper, manganese, and silicon. So, for example, SS316 contains chromium, nickel, and molybdenum. So 5 chromium, half molybdenum contain chromium and molybdenum. So XRF is very useful for confirming alloy families and detecting wrong material substitutions. So the next is blind spot of XRF. So now we must understand the very important limitations. So portable XRF cannot read carbon and boron. So this is clearly mentioned in the slide as blind spot. So this is very important in material verification. For example, carbon content is important for distinguishing certain grades of carbon steels and low alloy steels and stainless steel variants. If carbon percentage is critical, XRF alone may not be enough. In that cases, another method like OES, optical emission spectroscopy, may be required because OES can measure carbon. So remember, XRF is excellent for many alloy elements, but it is not suitable for carbon and boron measurement. So this is the most important points for inspectors. And the next one is surface preparation. Surface preparation is very important for XRF testing. So grid clean 60 to 80 grid contamination skews result. So this means surface should be properly cleaned before testing. If the surface has rust, scale, or paint, or oil, coating, dirt, weld spatter, or contamination, the XRF reading may be wrong. Why? Because XRF reads the surface layer. If the surface is contaminated, the instrument may detect the contamination instead of the actual base material. Okay. For example, if the surface has rust or scale, the result may show wrong iron or alloy content. If the surface has coating or paint, the result may not represent the actual metal. That's why grinding is recommended. Normally, the surface is ground clean using 60 to 80 grit abrasive. After grinding, the surface should be clean metallic surface. Okay. Let us look at diagram 2. So this diagram gives three important messages about XRF. So first it shows the detection range. It says XRF can detect manganese to uranium, manganism to uranium. The bar shows many alloy elements like manganism, aluminium, silicon, phosphorus, sulfur, chromium, iron, nickel, molybdenum, and uranium. But below that, there is a warning: cannot detect carbon or boron. This is the blind spot of XRF. Okay. Second, the diagram shows surface preparation is essential. On the left side, the surface is shown as contaminated. It may have rust or scale. Okay. This can give a wrong reading. On the right side, the surface is shown as ground clean. After grinding with 60 to 80 grit, the result becomes more accurate. So this path of diagram tells us good surface preparation gives reliable PMI result. Poor surface preparation can mislead the inspector. Okay, and the third diagram shows safety message. So non-intrinsically safe plus radiation, follow hot work and local radiation rules. So portable XRF uses X-rays. So radiation safety precautions are required. Also, the equipment may not be intrinsically safe. So in hazardous area, we must follow site safety rules and hard work permit requirements and area classification also requirements. So the last and final topic is safety precautions. So portable XRF is very useful tool, but it must be used safely. The operator should never point the XRF toward any person. Hands and body parts should not be placed near the test window during operation. The operator must follow the manufacturer's instructions, site radiation safety and procedure, and local regulatory requirements. In operating plants, especially in hazardous area, we must confirm whether the equipment is permitted for use in that area. So safety is not optional, it is part of the PMI activity.
Thank you for watching this video. Please follow our page for more upcoming videos.